In 1859, it reached the telegraph wires. On the 1st of September 1859, an English astronomer named Richard Carrington was sketching sunspots when part of the group suddenly brightened into 2 points of white light. It lasted about 5 minutes. Another observer watched the same thing independently. They had seen a flare in ordinary visible light, which is rare. What followed is why it is remembered. Within about 17 hours, a great deal of material from the sun arrived at the Earth. The aurora, normally a polar thing, was seen close to the equator. People in the Caribbean reported it. In some places, it was bright enough to read a newspaper by at 1 in the morning. The telegraph network, then the only electrical system in the world, behaved strangely. Currents appeared in the lines with no battery connected. Some operators disconnected their power and kept sending messages on the current the sky was providing. Others got shocks. And some equipment sparked. The sun does this on a rhythm of about 11 years, rising to a busy period and falling to a quiet one, and it has been counted continuously since the 1700s. 1859 was an unusually large event, not a unique kind of one. Nobody had ever seen the poles. Everything orbits the sun in roughly the same flat plane, and we are in it. That means every telescope, every observatory, and almost every spacecraft has looked at the sun from the side, near its equator. We have watched this star for 400 years through glass, and we have never had a proper view of the top or the bottom of it. Getting out of that plane is extraordinarily expensive. Leaving the flat disk of the solar system means canceling a great deal of orbital motion, and one mission did it in the 1990s by swinging past Jupiter to be thrown out of the plane entirely. It flew over both poles and measured the magnetic field and the wind there. It carried no camera pointed at the sun. Only recently has a spacecraft tilted its orbit far enough to look down and photograph a solar pole directly. The first such images were released in 2025. They matter because the magnetic field at the poles is what flips at the turn of each 11-year cycle, and until now, the cycle has been modeled almost entirely from the middle of the star. The sun will not explode. Stars that end in a supernova are much heavier than this one. The rough threshold is around 8 times the sun's mass. The sun is not close to it and never will be. What happens instead is slower and already underway. As hydrogen in the core turns to helium, the core contracts slightly and runs hotter, and the sun brightens. It is roughly 30% brighter now than when it formed, and it goes on brightening by about 1% every 100 million years. In something like 5 billion years, the core runs out of hydrogen. The outer layers swell enormously and cool to a dull red. Mercury and Venus are inside that expansion with certainty. What happens to the Earth is genuinely disputed, because the sun will also have shed a good deal of mass by then, and the Earth's orbit will widen in response. The models disagree about whether the widening outruns the swelling. Then the outer layers drift off entirely, and what is left is the old core, about the size of this planet, glowing white, cooling slowly for a very long time. No explosion, a long expansion, a quiet shedding, and then a small white ember that lasts longer than everything that came before it.